Hi, welcome. I'm Old Doc Charles, and this is a video, a part of a series on railway infrastructure systems. And this is part one, where I'm going to talk about infrastructure systems and some track elements. Now, it's traditional to include an introduction, so here's an introduction. This is all the shit I'm going to talk about. And when we talk about the railway infrastructure, obviously, we think about the track, which includes the rails, the fastenings, the sleepers, the ballast, switches and crossings, otherwise known as S&C. We think about viaducts, tunnels, and bridges, and stations and depots, signaling, and you may need some electrification if you want to run electric trains. So here's our system railway from before. So we have these more boxes, and in this video we're going to talk about the infrastructure. And if we zoom into that, and what we see is even more boxes. And these boxes are the functions of the infrastructure. So first we have the guidance force. So it's the lateral guidance of the train as it runs along the tracks, around curves and shit, keeping the train within its kinematic envelope. We also need to control the motions of the trains through areas with variable geometry. That would be your switches. We also have to support the loads. We need to provide a horizontal and vertical alignment that's in line with both the client and stakeholder requirements, if you remember requirements from before. We need to carry and distribute the wheel loads along the track bed. And we need to provide a smooth surface for an acceptable ride quality. We need to resist these forces. So we need to resist the lateral curving forces, because you don't want the track to shift in that. We need to resist the longitudinal traction and braking forces. And we also have to resist the micro forces generated by the slip between the wheel and the rail that create things like rolling contact fatigue and all sorts of crap like that. Now we need to transmit the forces between the train and the subgrade and the structures. We need to accommodate loading and unloading. So we need to provide easy and safe locations to permit boarding and alighting of passengers. And we need to provide safe and secure locations for the loading and unloading of various types of freight. We also have to provide maintenance. So we have to provide locations where we can maintain and store rail vehicles. That would be depots and yards and shit like that. And we also have to limit the environmental impact. So we want a smooth and tightly controlled running surface to minimize train noise and vibration, which will upset the neighbors and cause you no ends of complaints and problems. We also need to facilitate train detection. The signaling system, it needs to know where the trains are. And for that, we use like track circuits and axle counters. And we need to provide energy to power the trains, either by overhead line or third and fourth rail systems, depending on your individual railway. Right, so that's basically the, railway infrastructure system, and I'll talk about some of these things in future videos. Some of them I can, put two things together in one video. Some things have to be kind of separate. So we'll see how we go on, yeah? Right, so moving on. Right, so this is basically the words of what I just said. So I just said all this crap, and I said all this crap as well. So if you need to pause the video and write it down or memorize it or whatever, yar tis. So now I'm going to talk about basic track systems. And when we design track, we need to make sure that it's safe. So we need to provide an infrastructure that really can carry all the specified loads without damage or collapse or anything horrible like that. We need to provide an infrastructure that gives us a horizontal and vertical alignment that minimizes the risk of overturning and derailment and other bad things. We need to provide an effective infrastructure that offers the required horizontal and vertical alignment in order to give the right level of passenger comfort. Remember, it's a rail transportation system. It's not an amusement park ride. And we need to provide an infrastructure that's reliable and maintainable to a standard. Yeah, because, we need to make sure that the railway is fixable. We need an efficient railway. So it needs to be cheap-ish to build, affordable, and it also needs to be maintained at a reasonable cost in the long term. And we need to provide an infrastructure that we can maintain without too much downtime for the operator, whether that's a separate operating company or an operations department within the same railway. It depends on your individual railway. We need to provide a railway that has good routing and environmental performance. So we need an infrastructure that serves all the stakeholders without causing undue damage or impact on the environment. Let's look at what the track system consists of. Well, here we have some land, and we need to make a flat spot to put the railway on. We bring in some diggers and some navvies and create the profile for the track. In doing so, we create these artificial slopes. This one is generally referred to as a batter slope, and we call this an embankment. We put some topsoil on these, and then we plant some trees and vegetation to stabilize the slopes. Some railways also put up fencing to deter trespassers, livestock, etc. From getting onto the railway. Drainage needs to be installed to protect the tracks from flooding, both next to the tracks and at the boundary. This is where we're going to put the tracks. This is called the subgrade. And depending on the subgrade stiffness and the properties of the subgrade, we may need to install what we call a capping layer that alters the properties of the subgrade. You'll note the subgrade also slopes slightly in order to help draining. On top of the capping layer, we put a blanket layer. Typically it's sand. There may also be a geosynthetic material which we install to prevent water migration. Then on top of that goes the ballast, and then the track, which is the sleepers, the fastening, and the rails. We need a cess, which is a walkway next to the tracks for the safety of people that have to walk along the railway. We put in cable troughs because they're needed to carry the cables that connect the signaling. And we place signals, which are there to tell the driver if the line ahead is clear. Of course, many railways are replacing line side signaling with in-cab signaling. May wish to add some electrification if, we want to run electric trains. Most new railways use an overhead contact system with the contact wire held up by masts. Yeah, that's the track system, and I'll expand on these in later videos. Right, so The track system really, there's three things that affect the track. So what you've got is you've got the loads, which is, how heavy the trains are and how fast they go. The faster a train goes, the more loads it applies to the track. You've got the durability, which is, how long the track can go before it needs maintenance, sort of how well it stands up. And you've got the ride quality, which is, what the passengers want, a decent ride quality. And if you change any one of these things, it's going to affect the other two. For example, if you increase the loads by making the trains heavier or going faster, then the durability is going to go down, which means the track is going to need more maintenance, and the ride quality is going to suffer as well. So these three things are all interlinked. Now, track is often referred to as the permanent way, and it's called that. Basically what happens is that construction tracks are laid once the roadbed has been completed, and this is to allow easy transport of materials and equipment, and we call this the temporary way. We then construct the final tracks, and this is called the permanent way. So here, the picture on the right, you can see the temporary way, which is just basically some track panels, kind of like a train set that have been laid, and we can use these to bring in the maintenance, the construction equipment in order to build the railway. And then, once we've got all the ballast and everything down, then we can then build the permanent way, which is at the top of the picture. And the temporary way, like I said, it's just like track panels, and it's kind of delivered on these gizmars, is what they're called. That's the name of the company. And they kind of pick the track panels up and they shuffle them along on the rails that are going to be used for the permanent way, and lay them then in position where they're then kind of bolted together to build the temporary way. So track is made up of various elements. So we've got what we call plain line, which is just track, and it's tangent track, which is a fancy name for straight track. We've got curves, which are like curved track, and we have things called transitions. We also have switches and crossings, which we abbreviate to S&C, and again, that allows the trains to change tracks and cross over and shit like that. Track is made up from four fundamental elements. We have straight track, also called tangent track. It has zero curvature. It's just straight, really. We also have a circular curve, and circular curves have a constant radius. Then there's what we call a transition. A transition has a variable radius. Depending where you are along the transition, everywhere the radius will be different. And we also have what we call switches and crossings, which we also refer to as S&C. And these are elements with time variable geometry that allows us to move trains from one track to another. We join all these elements together in order to form a route. Now, track elements must always connect at what we call the tangent points. I'll kind of explain what that is. If you consider this circle, a tangent line is a line that's in contact with the circle and is perpendicular to the radius of the circle at the point of contact. And this is a tangent point. It's absolutely vital that track elements connect at tangent point, because not doing so creates the discontinuity called a kink. Kinks are very bad on the railway because a sudden change in track direction is a severe derailment risk. So tangent track is the easiest to lay out because it's just straight. It's the easiest to construct because it's just straight. And it's the easiest to maintain because it's just straight. It also sees the least forces from the trains. These are generally just longitudinal because the train is only going along. It's not really changing direction side to side. So there's some tangent track there, and you can see it's just straight, and hopefully down at the bottom there something happens so it doesn't crash into that mountain, but maybe it does, we don't know. And we use curves to change the direction of the railway. So we have horizontal curves to change the direction from side to side, and we also have vertical curves to change effectively the gradient or the up and downness of the railway. In some curves, the horizontal curve, the outside rail is raised slightly, and this is called cant, or super elevation in some places. If you have a tight curve, you may want to put in what they call a check rail on the inner rail to reduce the forces on the outer rail. And railways have limits on the amount of cant that you can apply. There's a maximum amount of cant that you can apply. There's a minimum amount of cant that you can apply, and some railways you can only apply cant in multiples of a certain number. Usually it's kind of 5 millimeters or so. There are exceptional values where the maximum cant can be exceeded in certain circumstances, and your railway administration, will have somewhere a standard that tells you what you can and cannot do. There are uncanted curves, usually diverging tracks in S&C, and low-speed tracks in yards. Tramways can have negative cant because really they have to stay level with the road, and if the road has negative cant, then the tram tracks will have to be negatively canted as well. So here's a curve, and you can see the check rail there. It's just inside the inner rail, and that's there because when the train goes round the curve, the back of the wheel will bear against the check rail and stop undue force on the outer rail. And there's a vertical curve, and you need to put in vertical curves because even though they're both straight, you still need to meet at a tangent point. And if you just had, an upgrade and a flat grade and they come together, there wouldn't be a tangent point. So you have to have vertical curves. In a curve, the outer rail is raised in order to reduce the lateral track forces. And we call this cant, or sometimes it's called super elevation, depending on what railway or administration you work for. We measure cant as the height difference between the inner and the outer rail. And there's a complicated formula to determine the lateral track forces, and it's kind of based on Newton's second law. Force is equal mass times acceleration, where the mass is generally taken as the axle load, and the acceleration is the lateral acceleration from the complicated formula. Now, to work out the lateral acceleration, we need to determine the angle that the sleepers are inclined at. Now, trigonometry says that the angle, alpha, is sine to the -1 of the height over the length, where the length is the distance between the rail centers. But for standard gauge, we have a trick. For every 25 millimeters of cant, you get 1 degree of inclination. So you don't have to do all the complicated trigonometry. So how much cant do we apply? If you look at the complicated formula, really apart from the cant, the lateral acceleration depends on the train speed and the curve radius. Now if we keep the train speed and the radius constant, then for a particular amount of cant, the lateral acceleration will be 0. So the forces will be directed downwards into the track, which reduces wear and tear on the tracks. This is called the equilibrium cant. And you'd think this would be the ideal situation. And for freight trains it is, but not for passenger trains. And I'll explain that next. Yeah, so like I said, freight trains work best with equilibrium cant because it reduces the track forces. But passenger trains are different. And this is because if a passenger train goes around a curve at equilibrium cant, it causes motion sickness to the passengers. And this is due to the fact that there's a discrepancy between the eyes, which see the train going around a curve, and the inner ear, which acts as the internal accelerometer, and it doesn't detect any curving forces. So this causes motion sickness. So what we do is we apply less than equilibrium cant, and that gives some lateral acceleration, and this improves passenger comfort. And the difference between the applied cant and the equilibrium cant is what we call cant deficiency. Now there are limits on the amount of cant deficiency that you can have. There are separate limits that apply to both plain line and S&C. There are, of course, exceptional values that can be used in certain circumstances, and your railway administration will have a standard that tells you what you can do and what you cannot do. There is another situation that exists, and this is when we have too much cant. And this is something that is not designed for, but usually occurs when a train is on a curve and slowing down because of a speed restriction or preparing to stop at a station or a red signal. As the train slows down, the equilibrium cant, cant deficiency, and lateral acceleration all decrease. Eventually, the equilibrium cant equals the applied cant, so the cant deficiency and the lateral acceleration become 0. Continued slowing further reduces the equilibrium cant, and the difference between the equilibrium cant and the applied cant is what we call cant excess. The lateral acceleration is now directed towards the center of the curve, and this is very uncomfortable for the passengers. Now, transitions are curves of changing radius, like I've said before, and they're there to limit what we call the jerk. And it allows the cant to be applied gradually. There's different formulae for transitions. They can be a spiral. They can be a cubic parabola, which is, quite simple. Or they can be what they call a clothoid, which gives a constant jerk. The cant is applied linearly. It's applied as a gradient, usually 1 in something, or applied as a rate of change of cant, which is based on the line speed, so it's so many millimeters per second. Your railway administration will have a standard that tells you what you can do and what you cannot do. So there's a transition there. You see, they're kind of hard to kind of pick out. You know, the train here that is on the curve, and there's a bit of tangent track further on, and there's a bit of a transition there, but, you know, they're really hard to pick out. Most railways, sensible railways, mark them. So if you look between the sleepers, or look on the sleepers between the rails, you'll see where transitions start and finish. What the fuck is jerk, and why do we need to control it? When you learn about physics in school, they teach you about, you know, distance, velocity, and acceleration. Distance is just how far you go. Normally it's measured in meters and denoted as x. Velocity is just how fast the distance is changing, or more formally, it's the rate of change of distance with respect to time, written as dx by dt, sometimes simplified as just x dot, and it's measured as meters per second. Acceleration is how fast the velocity is changing, or more formally, it's the rate of change of velocity with respect to time, written in terms of distance as d2x over dt squared, sometimes simplified as x double dot and measured as meters per second squared. So jerk is just the next step, and it's how fast the acceleration is changing, or more formally, the rate of change of acceleration with respect to time, written in terms of distance as d cubed x over dt cubed, sometimes simplified as x triple dot, and it's measured as meters per second cubed. Now, jerk is important for passenger comfort. Passengers can tolerate acceleration, but they don't like to be jerked. So there's limits on the maximum jerk that you can apply to a passenger. And whatever railway administration you work for, there will be a standard somewhere that gives you that information. Right, so that just about wraps up this. There's a recap. This is all the shit I've talked about. And yeah, that's all really. In future videos, I'll talk about some of the other subsystems of the infrastructure and some other things. I'm not really sure what I'm going to do yet, but you know, that's how it goes. Anyway, yeah, thanks for watching and that. Yeah, I think that need be all.
Jerk example. A fucking skint metro has a braking rate of 1.2 meters per second squared. When the bloody driver wants to stop the train, they move the braking handle to the service position. It takes the poxy brakes 2 seconds to fully engage. What is the goddamn jerk? Jerk is the change in acceleration divided by the change in time. The change in acceleration is from 0 to 1.2 meters per second squared, and the time it takes for this change is 2 seconds. Therefore, the goddamned jerk is just 1.2 divided by 2, which equals 0.6 meters per second cubed. So there.